Hi, so this is problem 4.4 at page 211 regarding applying conservation of mass principle. So in this problem we are given a data are provided for the crude oil storage tank shown in figure problem 4.4, which I will show in the next slides. The tank initially contains 1000 meter cube of crude oil. Oil is pumped into the tank through a pipe at a rate of 2 cubic meter per minute and out of the tank at a velocity of 1.5 meter per second through another pipe having a diameter of 0.15 meter. The crude oil has a specific volume of 0.0015 meter cube per kilogram. Determine A, the mass of oil in the tank in kilogram after 24 hours and the volume of the oil in the tank in meter cube at that time. So first thing, let's see what is given and what we need to find. So here we have a storage tank. Inside the storage tank is a crude oil and the state of this matter is liquid. Initially, the crude oil is at a volume of 1000 meter cube and a specific volume of 0.0015 meter cube per kilogram. At inlet number 1 or at inlet pipe 1, the volumetric flow rate Q sub 1 is equal to area times velocity. The volumetric flow rate given is 2 cubic meter per minute. At the exit or at pipe 2, the crude oil velocity exiting at 1.5 meter per second and the diameter of pipe 2 is 0.15 meter. In A, we are asked to find the final mass. So remember, the initial time is 0 hours with given this volume and this specific volume. When at inlet we start pumping the crude oil into the storage tank and at the exit the crude oil start exiting, after 24 hours we want to know what will be the mass, and the same thing for the volume. So this is the figure that we talked about in the beginning. So here we have a crude oil. The specific volume is 0.0015. The volume is 1000, and at pipe 1 we have a constant volumetric flow rate of 2 cubic meter per minute. We start pumping it into the storage tank and the crude oil start exiting at a velocity of 1.5 meter per second, and the diameter of pipe 2, this is by mistake, this should be 2, equal to 0.15 meter. So remember, the initial time is 0 hours, the final time is after 24 hours. At this initial time, the crude oil will have an initial mass, and after 24 hours, the crude oil will have a final mass. And the difference between these two masses is this, which is the change within the control volume in 24 hours. So since we are dealing with, or this problem is related to applying the conservation of mass principle, so let's write down the conservation of mass principle equation. So here we will take the delta time, move it to the other side of the equation. Next, we will take the integral of both sides of the equation with the limits. So the change of mass within the control volume is the final mass over the initial mass. And the mass flow rate is the final time and initial time. So this is a simple integration. So here remember the antiderivative of dm, or similar to delta x, is m. So it will be final mass minus initial mass equal to the mass flow rate entering minus the mass flow rate exiting. This is a constant value. It will exit the integral, and we take the integral of delta t, which will be t, and remember the initial time is 0, so it will be the final time only. So here our goal is to find the final mass. So let's see how can we solve this. Now what about the initial mass? Now we know that specific volume is the initial volume over the initial mass. So we have the initial, we have the specific volume, and we have the initial volume. We can solve for the mass in here, and we can get the value for the initial mass. Now what about the mass flow rate? In the problem, we are at pipe 1, we are given a volumetric flow rate, and at pipe 2 we are giving area and diameter. So velocity and diameter. So how can we get a different expression? Let's take a step back. What is mass flow rate? Mass flow rate is density times area times velocity. And what is area times velocity? As we mentioned in the second slide, area times velocity is volumetric flow rate. So we can rewrite this equation as density times volumetric flow rate. Now, since we don't have the density of the crude oil, but we have the volumetric, we have the specific volume, and the specific volume is the reciprocal of density, and so we can rewrite it in this way. And remember, the Q is area times velocity. So now what we did in here is we rewrote this equation. So we said that the initial mass can be solved by taking the initial volume, dividing it by the specific volume. And regarding at pipe 1 or inlet, we can find the mass flow rate by taking the volumetric flow rate, dividing it by specific volume. And regarding pipe 2, we don't have the volumetric flow rate value, but we have area and velocity. We have diameter, which we can find from it. We can find the area, and we have the velocity, dividing it by specific volume, and we have the final time, which is 24 hours. So here we rewrote the equation that we did in the last slide again, and now what we will do is we will plug in the given data so we can find the final mass. So as you can see, in red is what we want to find. The initial volume is 1000, the specific volume values is 0.0015, and Q1 is 2, and here we use the conversion factor. 1 minute is equivalent to 60 seconds, and the area, we have the diameter, which is 0.15, and the area of a circular cross section is pi over 4d squared. And here the 24-hour, we convert it into seconds. Plug this into your calculator and we will get the following values. So the final mass will, so we rewrote the previous equation in this way, and now we can solve for the final mass. And that will be the final mass value. And that's a solution for A. Next, we want to find the final volume. And by utilizing the equation for specific volume, which is volume over mass, we found the final mass. We know the specific volume. We can solve for the final volume, and that's what we did in here. Then we're going to plug in the given data and the data that we found, and the solution will be, and the final volume will be 1589.77, and that's the answer for B. Now I understand that this problem can have multiple different ways to solve it. As a practice, you can do the other ways if you want. Thank you very much. Have a good one.